All right, so we are going to begin our lesson on solutions in net ionic equations. Now, we already spent some time balancing and writing net ionic equations, but this is going to give you a little bit more of a structure as to how to do them. So, reminder before we get going, solutions are homogeneous mixtures. A homogeneous mixture could be a mixture of solids, liquids, or gases. It just has to be evenly spread throughout or evenly distributed throughout to be called homogeneous. As long as the two things that you're mixing, you have a solute and a solvent, you can call this a solution. Now, for our purposes, for net ionic equations, what we're going to be really referring to when we use the word solution is aqueous solution. And what I mean by that is we've taken a substance and we've dissolved it in water. So most of the substances that we're going to be dissolving in water are going to be ionic substances, hence net ionic equations. So let's get started. Why the heck do we even have these things called net ionic equations? What's the difference between a regular chemical equation? So sometimes when you're mixing solutions and you get what's called a displacement reaction, a product may not really appear in the physical chemical reaction. And the reason for this has to do with the solubility of ionic substances in water. So there's a picture right here showing the formation of a yellow precipitate. You've seen this demo before in our class way back when at the beginning of the semester. Let me change my color here to something bright. This reaction can happen a number of different ways. We can form this precipitate a number of different ways, but in our class, what we ended up combining was lead nitrate, so PbNO3, 2, and potassium iodide. Oops, potassium is not a P, it's a K. Potassium iodide. And both of these were aqueous solutions. They were both dissolved in water. And when we mixed them up, what we ended up getting was the formation of this yellow substance, which is actually lead iodide. Lead iodide. And the potassium and the nitrate were still dissolved in solution. So they were just floating aqueous ions, which we don't really include in the product side of the equation because they don't really play a role in the reaction. They are called just spectator ions. They didn't combine and form new bonds. They're essentially just floating around in the solution. So since we wouldn't include them in the product side, that also means that we have to decide, are we going to even include them in the reactant side? Is it worth saying that potassium and nitrate were even present at all if it's just the lead ion and the iodide ion that we're reacting to make lead iodide? So this is why we have net ionic equations. It's really with the interest of only writing the species in the reaction that are actually reacting and ignoring the other particles that are not participating. Now, the ones that are going to react and form a substance or form a precipitate are insoluble. I always have trouble spelling precipitate, so I really have to focus here. Precipitate. Precipitate. Beautiful. So lead iodide is a precipitate, meaning it's a solid when it's in a solution. That means that it's insoluble. Specifically, if we're talking about aqueous solutions, it means it's insoluble in water. So this is why the reason for net ionic equations has to do with solubility. The substances that are insoluble are going to be the ones that are forming bonds together and actually participating in a reaction. So for the purpose of this class and for the College Board, for AP, you've got to know a few solubility rules. And this list actually goes a little bit more in depth than we even need to go. So what we need to know is that any substances that involve the group 1 alkali metals are going to be soluble. So let me give you some examples that the College Board expects you to know. Anything bonded to sodium and potassium are going to be soluble. Anything involving a nitrate is going to be soluble. So nitrate is the NO3 minus 1 anion. So any ionic compounds involving this polyatomic ion are going to be soluble. Any compounds involving acetate are going to be soluble. Now, this is not something that you need to know for the College Board. So the College Board expects you to know that sodium and potassium are going to be soluble compounds. Nitrate is going to be a soluble compound. Acetate is a special polyatomic ion. There's two different ways to write it. This is the way that I learned and in school, but now it's more common to see it written this way. It doesn't matter, it's the same thing, but any compounds, ionic compounds involving acetate are soluble, so that's just good to know. And then any ammonium compounds. Ammonium is your NH4 with a +1 charge. Those are going to be soluble, and the College Board does expect you to know this. So it's also good to know that most chlorides are going to be soluble except for those involving silver, lead, and mercury. In fact, it's a good rule of thumb to assume that any ionic compounds, or for the most part, we can say any ionic compounds involving these are going to be insoluble. The only time that we're going to see compounds involving silver, lead, and mercury that are soluble is when we're bonded to a group 1 alkali metal, a nitrate, ammonium, or an acetate. So essentially, I'm going to color code here. Let's see, let's do orange is bright. These rules have first priority, whereas the insoluble rule has second priority. So silver, lead, and mercury are only going to be insoluble if they're not bonded to alkali metals, nitrates, ammonium, or acetate. So let's move on. So what the heck determines solubility? We've talked about this, what causes things to dissolve in water, and we've talked about this whole like dissolves like. Water is a polar molecule, meaning that it's got a positive end and a negative end, and this allows it to cause ionic compounds to dissociate. So we've got this image right here that's showing that in action. This ionic compound looks to be sodium chloride. It's got that 1-to-1 ratio, but it could be any ionic compound that's got a 1-to-1 ratio. But what we're seeing here is that the water is actually starting to align itself so that its positive dipole is attracted to the negative ion, and its negative dipole is attracted to the positive ion. And this is causing those ions to separate because they were once attracted to one another, but now they're experiencing these attractions to the dipoles of the water molecule. And this is what dissociation is. So this is another great image showing that positive and negative alignment, but this is specifically with sodium and chloride, but it could be any positive and negative ion. So hydration is the process by which positive ends of water are attached to the negatively charged ions and vice versa. So these images we've just seen, we could call hydration. It's what causes salt to split when it's being dissolved in water. So when ionic salts are dissolving in water, they're actually splitting apart into individual cations and anions. So they're maintaining their charge. There's no transfer of electrons. They're truly just separating apart. So the solubility of ionic substances really depends on the attraction between the ions before you put them in the water, and then the attraction between the ions and the water molecules. You might be wondering, what the heck does that mean? Whichever attraction is greater is going to be the one that is maintained. Greater attraction is the one that's going to stick around. So we've talked about how some processes overall can be endothermic and exothermic, but the steps in between are still going to be exo and endo. So what I'm saying by this is overall, the greater attraction is going to be maintained. So remember, it still takes energy to break bonds. So I'm still having to input energy to break the attraction between the ions. It's not something that's happening organically, I guess. It takes energy to do that, to break ionic bonds. But energy is released during the formation of bonds. So remember, the bonds between the ion and the water releases energy. release. So the formation of bonds releases energy. So as long as the change is very, very small, then the solubility or the dissolving will occur. We can talk a little bit more later in the course about what exactly determines whether or not the change is small enough. But for now, as long as we just have an idea that, you know, the more favorable attraction is going to be maintained, we'll be good to go for solubility. So polar and ionic substances are expected to be more soluble in water than nonpolar substances. This is that whole like dissolves like. An ionic bond is the essentially most polar dipole-dipole interaction. So that's why it would be dissolved in something that's polar. Non-ionic substances, such as ethanol, are soluble. So, moving on. Net ionic equations. So let's talk about some steps about how to write them. So if a product is soluble, it's going to stay dissolved in the aqueous solution. If a product is insoluble, it's going to appear as a solid precipitate. So in ionic equations, we're going to show the individual ions that exist in the solution. And the net ionic equation only shows the true product and the ions that reacted to form the product. So I kind of gave you guys a small taste of this when I was talking about that formation of lead iodide. So, some general steps. First things first, when you're trying to find the net ionic equation, you got to have, first of all, the balanced chemical equation. And we're going to include state subscripts, solid, liquid, gas, aqueous. Then we're going to break all of the soluble compounds into their ions. So here's what I mean by that. Oh, good, my marker is selected. Instead of saying NaCl, aqueous, we can do this for balancing the equation for our initial first step. But once we get to the second step, we're going to break this apart and say, okay, well, we know sodium chloride is soluble. That's why it's not a precipitate. So I'm going to write Na with a +1 charge plus chloride with a -1 charge, because this is what actually is happening in the solution. They're not connected like they once were. I've indicated the charge, and then once I've balanced my equation, I'm going to have to indicate the number of each ion. This is easy, though, because my formula is a 1-to-1. But let's say that I was working with potassium oxide. Shoot, I wrote the formula wrong. Let's try again. Let's say I was working with potassium oxide, aqueous. When I would write my ions, there would be 2 potassium ions with a +1 charge and only 1 oxygen ion with a -2 charge. So this is what they mean by indicate the number of each ion. And then obviously they're dissolved in water, so we would write aqueous after both of them. So anything that's a solid, liquid, or gas is going to remain unchanged because those are not dissolved in water. And then once we've got everything broken up into soluble ions, we've completed step 1, we've completed step 2, and we've completed step 3, we can start finally removing the spectator ions. So step 4. So let's see what this looks like. We've got this reaction right here. So step 1 would be balancing the equation and indicating the states. So when I balance my equation, I'm going to get a 1, 2, 1, 2 for my coefficients. Lead chlorate is going to be aqueous. Remember, lead is typically going to be soluble when it's not, or I'm so sorry, if it's bonded to these polyatomic ions we were talking about from the first page. Sodium iodide is aqueous, but lead iodide forms a solid, it precipitates. Sodium chlorate is going to be aqueous because it's a group 1 alkali metal, and those are always aqueous. So step 2 is going to be identifying the soluble compounds and breaking them up into their separate ions. So everything that is aqueous, I'm going to break apart into its ions. So lead chlorate is going to break apart into a lead ion and 2 chlorate ions. Sodium iodine is going to break up into a sodium and an iodine, but since there is a coefficient of 2, there's 2 of them. Lead iodide on the right side of the equation is staying a precipitate. It's not aqueous. And then sodium and chlorate break apart on the right side. So now what we're going to do is we're going to remove our spectator ions. So these are the ions that don't enter ions that do not enter into a chemical equation and are the same on both sides. So what this essentially means is they just don't participate in the reaction. So that's why they stay exactly the same before and after. So, just like if you were a spectator at a sporting event. So, chlorate is actually going to cancel out because it's the same before and after the reaction. It didn't participate in anything. And then sodium is going to cancel out. It's the same before and after. It didn't participate in anything. So what we're left with is the lead and the iodine before the reaction. They're both aqueous. And then after the reaction, they combine to make a precipitate or a solid. So your turn. You try. When you're done, you can unpause the video and check your answer with me. All right, so I'm assuming that if you've unpaused, you are ready to check your answer. Oops, shoot, let me go back here and select my marker. So first things first, I would balance my equation. So I'm noticing that I need 3 sodiums on the right side because I only have 3 on the left. And then, gosh, that's it. Is that it? Everything's balanced. Yeah. So that was easy. Now I'm going to start writing out what is a solid and what is a aqueous solution. So sodium is a group 1 alkali metal, so that means it's going to be aqueous with phosphate and chloride. Iron chloride is going to be aqueous because I remember that chlorides are aqueous with anything except lead, silver, and mercury. And then over here, my iron phosphate is going to be a solid precipitate. Now let's say that you were doing this, you're like, gosh, I know that all of these are aqueous for sure, but I'm not sure about this iron phosphate. If you're being asked to write a net ionic equation, something has to be a precipitate, something has to react, which means that if by process of elimination everything else is aqueous, this last compound must be a precipitate. It's the only thing that makes sense. Otherwise, there would be no reaction and you'd have no job to do. So now that I've got everything balanced and I've gotten all of my phases written out, I'm going to start breaking things up into their ions. So sodium phosphate is going to be 3 sodium ions that are aqueous plus a phosphate ion that is also aqueous. And then iron chloride is going to be iron with a +3 charge. I know that it's +3 because there's 3 chlorides bonded to it, and it is aqueous, plus 3 chloride ions that are all -1, which are aqueous. So these are my ions before. After the reaction, I'm going to have 3 sodium ions that are soluble and 3 chloride ions that are soluble, aqueous. And then I'm going to have my iron phosphate that is a precipitate. So now I'm going to start canceling out my spectator ions. I think if I change my color, I hope it doesn't make my writing go away, but my sodiums are going to cancel out before and after. My chlorides are going to cancel out before and after. And those are the only things that are spectators. So before my reaction, I had phosphate that was aqueous. Geez, I'm having a hard time. And then I had iron that was aqueous. And this yielded iron phosphate precipitate. And everything's all balanced, so I've done my job correctly. So now go ahead